So that is about all I have to say. I would now like to introduce our speaker, Larry Peterson. A little bit about him. He was born and raised on a farm in Nebraska. And in fact, you can usually find him and his fellow Huskers at the Fox and Hound most Saturday afternoons in the fall. He went to graduate school, got his PhD in computer science at Purdue. And he first came to Arizona as an assistant professor in 1985, joined the faculty at Princeton University in 1998, where he was head of the computer science department from 2004 to 2010, and then he rejoined University of Arizona in 2013. And he's also a professor emeritus at Princeton. So he is currently on leave from the UA and serving as chief architect at the Open Networking Lab, which is a nonprofit in Silicon Valley that's building open source software focused on opening the internet to innovation. And he actually came here today after his flight was canceled from San Francisco. He had to board another flight and drive all the way up from Phoenix to here. So we're very grateful that he made it. And while he was at Princeton, he co-founded a internet company that was acquired by Akamai, building software that speeds up content delivery from Netflix to ESPN. And fun fact about him, he's had Arizona basketball season tickets since 1986, which was 3 years after I was born. And when he's not following the Wildcats or Huskers, he's enjoying Tucson's music scene, and he actually volunteers at the annual folk festival. So tonight, Larry will discuss how software is eating the world. It's partly about the role software plays in today's digital world, but more generally about how software affects the pace of innovation. So without further ado, I'd like to introduce Larry Peterson. Thank you so much.
So it wasn't that traumatic, but I was a little nervous about getting here because canceled flights do that to you. So this series is about big data, and the big data guys have wonderful pictures they can show you because they visualize their big data. I'm not a big data guy. I'm the guy that makes the big data possible. All right, so this is going to be just a little bit different. I have a catchy title. Software is in fact eating the world. That actually is a quote from Mark Andreessen, who is now, he was the guy that wrote Mosaic, one of the very first web browsers. And then he's now a venture capitalist, and this was the investment theme of his VC company, 5 years ago. And I think we all recognize, when you look at it from in example form, what software eating the world means. Uber's eating taxis, Airbnb's eating hotels, Netflix has already eaten Blockbuster, and the list goes on and on. So this is basically what I'd like to talk about for the next several minutes is, what is that about, and why does it seem to be moving so rapidly? And as you heard, I'm on leave here. I'm involved in a software company, but it's nonprofit. It's open source, but this is open source as actually some people refer to it as weaponizing open source. It's how to use open source to cause shifts and changes in the industry. So let me just jump right into it. So a lot of people have a pretty straightforward notion of computing. There's hardware and there's software. So I'm going to start there, except I'm going to change these words a little bit. There's platforms and there's solutions. The platform is the thing you build the solution on. The solution is what you care about. It solves some problem for you. You could call it an application, but I'm going to call it a solution. Well, it turns out there's a virtuous cycle between platforms and solutions. And they keep cycling around and they keep improving each other. And there's a couple of external forces that come to bear. Users just tend to want more from their systems, from their computers over time. And the hardware guys, are still keeping pace with Moore's law. They're doubling the transistors every 18 months. Slowing down a little bit, but those are 2 bits of input that keep this cycle moving quickly. So what's happening is we keep building better platforms, and that enables better solutions, And then those solutions start stretching the capabilities of the platform, so we improve the platforms. And this is basically what the cycle is. So I could start this anywhere, and this is a little bit of perhaps revisionist history, but I'm going to start it in mechanical computing. It goes all the way back to various pre-electronic computers, analytical engines. There's various forms of these. Very early computers, and they had a solution. They were quite often used for ballistic calculations. And we want to fire more bullets, and that becomes a more complicated thing. So we need more power than the analytic mechanical computers were able to give us. And that is, in fact, one of the very earliest motivations for what turned out to be the very earliest electronic computers. So let's just call those mainframes. I'm kind of simplifying this, but just to give you a sense of how these things keep cycling. And so, well, we got mainframes, and they're doing a great job doing ballistics calculations and calculations of nuclear explosions and so on. But hey, we can use those for business applications. And of course, then we start to build more and more business applications, and sure would be nice if we could run those for our small businesses. And again, I'm simplifying, but then we get personal computers. And personal computers are great for these business applications. And you think back to the very earliest ones you had early spreadsheets and so on. But you can do other stuff. So you start playing video games. And those video games would be better if only I could play video games with my friends. And this is part of the drive that led for the internet growing. There's other things that happened as well. Well, now we got the internet, and so we can have Facebook, but now we've got thousands and thousands of cat videos, so we need a place to put them. So we put them in the cloud. And now that we've got the cloud, we can have Uber. So these things just keep enabling each other, and this cycle just continues. And in fact, just to tie this back to the theme, big data is the app that's taking advantage of the cloud. So I want to sort of explore that process of platforms enhancing solutions, solutions driving the next platform. And try to understand how that's limited and what we can do about that. And in fact, the theme of the Open Networking Lab again is to open things up to innovation. So what are the roadblocks? Well, I want to look into what these platforms and solutions are just a little bit more closely. So the platforms are in fact layers and layers of software. And it's only at the very bottom that you get hardware. So I could have taken any one of those platforms that I talked about. Let's just take the internet. Well, let's take a cloud, for example. The cloud there is definitely hardware there. There's warehouses full of tens of thousands of servers. So there's definitely hardware there. But what really makes that work is all the layers of software. And that software has evolved over time in response to the cycle that I was just talking about. And so layers upon layers of software has happened. The internet's the same thing. There are switches, but there's software that drives those switches. And then the application just happens to be the topmost layer of the software. That's the way I look at it. It's the one that the user interacts with. The user's quite often unaware of how many layers of things happen underneath. I mean, you can go to the web as a great example. The web was this wonderful application. You could browse it and get to all this information, but it only happened because the internet was already there, and it had been there for quite a few years, and that was just the next app that was built. And now the web itself has become a platform, and we're building applications on top of the web. It's the same idea. So yeah, you can draw an arbitrary line there, but the way that I look at it is it's software all the way down. So what is it that limits innovation? What limits innovation and the pace at which this cycle iterates is basically when the system becomes vertically integrated. And so you try to hold your hands around the whole thing and say, I'll give you this hardware, I'll give you the software, I'll give you everything up to the application as well, because I know best how to do that. And so I will vertically integrate the system. And there's always optimizations you can get out of that kind of design. And if you're the first player to the table, then you quite often have the advantage that leads to that. So that's what limits innovation quite often. So the key to accelerating innovation is, well, the platforms become software-based. They're not hardware-based. Hardware is the smallest, most unimportant element of these platforms. We're going to reduce the hardware as small as we possibly can. The interesting aspects of these platforms is that they're software-based. The platforms are open. They're not closed proprietary. Well, now we get into a whole argument about how you're going to make money off that. And every time this thing happens, somebody's business model breaks down and they go out of business, and somebody else's business model takes advantage of it and they do just fine. So this has happened many, many times over. But there's always an incumbent that's going to be displaced when you open things up. But like water running downhill, these things do become open over time because somebody makes it available. The platforms are disaggregated. That's the opposite of their bundled. And bundled basically says, I will give all these software stacks at one time, take them or leave them. I can't give you the individual pieces. The more I can break that down into smaller chunks, the more opportunity there is for other people to come in and play with subsystems and smaller chunks and innovate on top of those. And in the limit, and this is sort of the punchline of this, the hardware is commodity. And so that's what's basically happening. If you drive the hardware to commodity, the margins are very, very low, and it tends that you go buy it from, a couple of hardware vendors. Intel's a great example. But that commodity hardware is the basis, because once I have the commodity hardware, then I am now free to build all these layers of software on top of it. And so that is what the cloud is all about, right? We have reduced these many, many different types of computers that were available over the years down to a common commodity instruction set. The Intel instruction set is the great example. And you stack up tens of thousands of these in racks in giant warehouses, and that is how you build the cloud. And then it's entirely all these layers of software that turn that into some usable platform on top of which Uber and Airbnb and all the big data folks can do their thing. So this is where we end up then, is that this is the key to accelerating innovation, is that it is all these layers of software, the topmost piece of which is the application, and the bottommost thing is the commodity hardware. Now, I'm making it sound all very, very easy. There are lots of battles fought in getting to something that looks like this. And basically the market forces at play here is that there is a tension between wanting to aggregate and pull things in together and bundle them up, and then the counter force is to pull them apart and to reduce the hardware to commodity. No one wants to be in the business of selling commodity because their margins are so much lower. And by the way, just in case you haven't noticed, computer science is a very rich discipline, lots of great intellectual work that goes on, but it happens to be sitting right adjacent to a multi-billion-dollar industry that keeps churning away. And there's a really interesting interplay between the two. Quite a bit different than a lot of other industries out there, science disciplines. Okay, that's kind of abstract, but you maybe have some thoughts in mind as to examples, but I'm going to show you one that's pretty well known, which is the case of IBM. So you probably can't read the mainframe label, but it says IBM. And so now you know where this one's going. So it was once a time that you went to one vendor, it was the monopoly, and they built specialized hardware, and they built a specialized operating system, and then they would build specialized applications on that. And we know what happened to that industry over the last few decades. It transitioned so that there's microprocessors, and those have become commodity, and there are open interfaces, so we can all take advantage of those interfaces, and we can build layers of operating system software. And some of them are open, some of them are closed, but that's fine. We have options, and they have well-defined interfaces, and that makes it possible to build applications on top. And there's some other divisions in there. You go to Intel to buy your chips, but then you go to Dell to buy the chips packaged up in servers, and then and so on and so forth. So there are other divisions, but basically what happened, it was a transition from a vertically integrated, closed proprietary, slowly evolving system market into a horizontal open interface and much more rapid innovation. And the reason for the rapid innovation is instead of one top-down organization deciding what those apps are going to be, anyone who had access to the interfaces to, let's just take Linux for example, is able to build an app. Well, in fact, Mac OS is another great example. And I'm in the microprocessor replacing mainframes, but of course, those are now going to be leapfrogged by the mobile devices. That's where the economies of scale are in the future. And it's exactly the same thing. There are open interfaces. It's not necessarily the case that the The software layers are themselves open. Sometimes they are, sometimes they aren't, but the interfaces are open. And that's what makes innovation possible. All right, that's the computer industry, that's the past. What I'm going to spend most of my time talking about is what's going on right now. And now we're in the network industry. And so you can't read the label on that one, but you can imagine it says Cisco. And maybe you didn't realize routers were quite this big, but they're as big as mainframes. There are multiple racks of hardware in large networks routing centers. And the engineers would tell you it's not going to work if you don't have the specialized hardware. And on that specialized hardware, it's got to run our specialized operating system. And if you need a new feature from it, then we're the ones to give you that. It's exactly a repeat of the closed, vertically integrated proprietary system. And now, if you think about who uses these routers, it's the telecommunications industry. All right, they are waiting for the next 18 months when the next release of software comes out so that they can add a new feature and then turn around and bill all of us for it. But they're now slowed down, and to make matters worse, if you're, let's just say, AT&T and you've waited 18 months for the next rev of the software, Cisco or Juniper or Huawei or any of these companies aren't going to deliver it just to you, they'll deliver it to your competitors as well. So what happened here, just a little history, is back in the day, AT&T was the great innovator. They did a huge amount of innovation, but over time that was outsourced basically to the vendors, and they have lost the ability to do that, and we're now in the midst of a transformation that's trying to reclaim that capability back into the service providers or the network operators. So where that takes us is a very parallel kind of thing, which is we're going to start with commodity hardware, typically called merchant silicon switching chips, and that gets wrapped in a piece of tin called a white box switch, just like you wrap an Intel chip in a Dell box. So there's sort of equivalent thing going on, and there are vendors that will sell you the box and with the merchant silicon in it. And there's some open interfaces, and on top of that now is a set of controls of that hardware. Kind of like you would control a microprocessor, you're now controlling the switches. And on top of that, now we can put applications in the network. So we are providing solutions that are not running on microprocessors as your typical software. These solutions that we're going to offer run on the platform that is in fact the switches that are now programmable. And the instruction set is different. What you can tell them to do is different. You don't tell them to add and subtract and multiply and divide. You tell them to forward packets from here to there according to a set of rules. And that takes us to a place where it's a horizontal, open interface, rapid innovation. We're in the midst of this transformation right now. And it's called software-defined networking, or SDN. And so just a real quick picture of the way to think about it is not all that much unlike thinking of there being an operating system like Mac OS or Linux or Windows running on top of a processor, except it's a whole network worth of hardware, a whole network's worth of switches. So the switches now, we've broken that vertically integrated thing apart. The switches just do what they're told. They forward packets. All the smarts as to where they should forward them, and every policy decision that goes into that has now been broken out of that hardware, and it runs, guess where? In software somewhere else. And what we're going to define is an interface by which I can tell those switches what they ought to do. So this is the essence of software-defined networking, is I have an abstract forwarding model, and you can kind of think about it as the switching equivalent of an instruction set, the things that I can tell the hardware to do. And then I have an operating system, and one that I've been involved in a little bit is called ONOS, which stands for Open Network Operating System. So this is a wannabe Linux in the networking world. It's not there yet. There's a lot of things going on in this space, but that's kind of what it's trying to be. And like any good operating system, it gives you some abstractions that you can write programs to. So you're still writing applications, but instead of them being applications that are trying to manipulate switches, they're applications that are trying to operate and do computations and run algorithms on graphs. because that's the abstraction that we're going to raise a global network map out of the hardware underneath. It's a higher level abstraction that we can program to. It's no different than being able to work with a file instead of a disk. You don't have to know what sector a bit of data is on. You're working with an abstraction called a file, or directory, same idea. Well, so software-defined networking started about 5 years ago and started to get some traction. It really has recently. In fact, if you Google software-defined, you will find a really long list of examples. Software-defined radio, software-defined power, software-defined every platform that you can imagine. These are typically this is applied to platforms. You can make it software-defined. And it is literally happening everywhere. And this is kind of the counterpart, or just another way of saying software is eating the world. Everything is becoming software-defined. But it was always the case that the applications were written in software. What's changing is that the platforms that those applications are written on are now being more and more written in software. And we're pushing the hardware down to a very base commodity. And that's when you get to scale and build clouds, build entire warehouses full of servers. Okay, so this is what's going on. Interestingly, the trailing end of any industry out there that's becoming software defined is the telco industry. And so what I'm going to talk about for a few minutes is software defined telecom. And don't interpret that too narrowly. It could be cable company, Comcast, AT&T, Verizon, the people that bring you the internet. And I'm going to talk about a particular thing called a central office, and it's completely misnamed because it sounds like it's a giant central place. The central office in the telco world is the very, very edge of the telco network. It is the small branch office that you might drive past, a small brick building with Verizon or AT&T on it, and it's sitting on some corner in your neighborhood. That is the central office. There are thousands of them in the US. So they're not at all central, but that's just what they happen to call them. And so this is kind of an introduction to the project that I'm working on, which I'll talk a little bit more about, called Cord. But this is a telco newsletter called Fierce Telecom. But it says AT&T proceeds with Cord field trial in Georgia, submits virtual OLT specs to Open Compute project. So the first thing I have to warn you is once you step into the telco world, it is just littered with acronyms. And I'm going to try to keep you up to speed on them. And Cord is itself an acronym. It's a really good acronym. It stands for Central Office Re-architected as a Data Center. So we're trying to take the technology that I've just been walking through, commodity, everything software, and bring it into this building that has been full of machines that have collected over 50 years. Walking into a central office is like walking into a telco museum, and it makes complete sense because if anybody, this equipment's been paid for, if anyone is getting use out of it, it's basically printing money for the telephone company, and they don't turn it off. But it is actually starting to slow them down, and this is something that they have to address. Now, and this is a project that comes out of the ON Lab, or Open Networking Lab. So just to kind of emphasize this, because I don't have a really good picture, I'm going to show you a different picture. When you think of a network, you quite often think of the giant backbone network of a company like AT&T. And this is a picture I just grabbed an hour ago, and it's actually quite dated, but it's the kind of picture where you can imagine these giant routing centers in major cities in the US. We call them the NFL cities, basically, and then there's fiber between all of them. And that is in fact the backbone. And it's a huge thing, and it's clearly I could model it as a graph, and networking is all about how do I get packets from point A to point B across a network like that. That's where the interesting algorithm is, but this is not where the costs are. This is well understood, cost effective. That's not where their problem is. The problem is when you see the commercials about, can you hear me now, when they show you their maps colored red and the other one's yellow and it doesn't quite cover. The way they got that coverage was thousands of these central offices around the country. That's where their costs are. And so these central offices, or COs, is the other end of the fiber on the last mile of your internet connection. And if you've heard the term last mile or fiber to the home, it is the central office at the other end of that fiber, or of the coax. And again, the cable company calls it something else. But it basically is the service provider's gateway to their customers. Like I said, there are thousands of them in the US. AT&T alone has 4,600 of these around the US. They support 10,000, maybe 100,000 customers, and even the cell towers come back to them with their backlinks. So that is the very edge of the internet that is offered then to you and me. Enterprises connect to it as well. Well, it's interesting also because it's an incredible vantage point for people providing internet services, whether it be gaming or Facebook or Netflix or YouTube or whatever. If they could just get that point of presence, think of how close they are to you and how much better the service they could offer you. If only those buildings were like little data centers and they could spin up new services very, very quickly in the same way Google and Microsoft and Facebook can in their data centers. So the challenge is it's really expensive, both in terms of capital expenditures and operational costs. It is not at all programmable, and that is what's going to slow down innovation. Every one of those boxes that fits into a central office is vertically integrated. And they're just impossible to crack open, and you basically have to wait a long time to get new functionality into them. And that's what is basically slowing down the ability to offer new services. So what CORD is trying to do is to bring the economies of a data center. Remember, we're using commodity hardware, a very few number of building blocks. And when you talk about a switch, we call them white box switches, and the agility of a cloud provider. And that is that the software is what makes this thing run. That the picture of all those layers of software from before. Now, if you've ever gone to the cloud, all of you use the cloud indirectly through the cloud apps like Gmail or Facebook or whatnot. But behind the thing that's running on your phone is massive software running back in some data centers. And there's storage, and then you would build a mail system on top of the storage, for example. So what we're trying to do is add a new kind of service to that, which is access as a service. That of all the things that you could do with the cloud, you want to have the cloud be the thing that brings you your internet access in the first place. So it kind of bootstraps the whole thing. So this software as a service is an interesting point. If you haven't heard it before, it is another way of saying software is eating the world. But it's not eating the world because I shipped you software and then you installed it on your computer. That doesn't make any sense because your computer is becoming less and less important. Aside from this, it's the computer that lives in the data center that's important. And so I don't have to ship you software to install on the computers in the data center. I just have to offer that software to you as a service. So you don't install an email application on your PC. You subscribe to the email service. Everything is being offered as a service. Uber is offered as a service. Airbnb is offered as a service. You don't, yes, there's a little app, but all that really was a little tiny specialized web browser. It's all it really was. And so now imagine access as a service is what we're trying to get to. So what this turns into then is to take, kind of hard to tell, but row after row after row of specialized hardware. I mean, like I said, up to maybe 300 different kind of devices in a central office and transform it into exactly the same architecture you would find in a data center, which is to say commodity, 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 and we're going to put some open source software on top of it. Now, just to walk you through a little bit more detail of what is in a data center and then why this is going to be a little bit different when we do it in the central office. Basically, we've got racks of servers. A rack might hold 30 to 40 servers, and some of them are going to have storage on it. And then we're going to interconnect them with a switching fabric. And this is basically a way to get data from one computer to another within that data center. And then the whole data center as a whole is connected by routers to the rest of the world. So when you go to an Amazon data center, you've come in through a router off the internet, and now you're in a warehouse-sized computer. You can actually, if you imagine that it's you've been miniaturized and you're walking through the aisles of a computer, and instead of a CPU, it's a server, and instead of a spinning disk, it's a disk blade, but it's basically a computer. It's got all the parts of a computer, but now inside of a warehouse. So one of the problems with this data center is the care and feeding of the connection to the internet, because that is the lifeblood to get you out to the rest of the world. Every time you do Gmail, you got to get into somebody's data center somewhere. So they're treated like pets and take incredible care and feeding, and the amount of bandwidth they get you out is, while a very, very large number, it's not a large number considering all the people that make use of it. And in fact, the real problem here is that the structure of that switching fabric that gets you from the top of rack, from one rack into another rack, is the lion's share of the bandwidth. The east-west bandwidth is the lion's share of the bandwidth. It's the north bandwidth that gets you out to the rest of the world is actually quite thin. And that's just not going to work at the edge, because at the edge, it's getting into the central office, i.e. getting into the data center, that is in fact the challenge. And so what we're going to do to address that is we're going to take that northbound interface and we're going to just bring it down and treat it like any other part of the commodity cloud. And so we're going to have a bit of it sitting at the east end, and we're going to have a bit of it sitting at the west end, and that's going to connect me to your home, and it's going to connect me to the backbone that I showed you the picture of before. And now the data can flow east and from east to west across that. And in fact, whoops, I lost my animation here. Maybe it comes up next. I just forgot where it was. We're going to treat those like cattle. So basically, they're no longer pets. We just got racks after racks of the ability to do I/O. And so now the data comes in, and I'm not showing you the home over on one side, but it's there for your enterprise. You come in and you hit an I/O device, and then you bounce up into the switching fabric and across, and I got all that east-west bandwidth available to me because I've got so much parallelism going on that I get good access behavior. And by the way, those switches are the kinds of switches I was talking about before. They just forward packets as they're instructed. The brains of the system that tell them how to do the forwarding is actually now running on a server or a set of servers inside of that data center. And I've just introduced a little term here I need to spend a second on. It's running in what's called a VM, or a virtual machine. So a virtual machine is a technology that makes it possible to take a single physical machine and make it appear to different users to be their own private virtual machine. It's as though I have rented a machine from Amazon's cloud, even though technically I was sharing a physical machine with some other people, but it behaves just like a virtual. It's a virtual machine, but it behaves just like a physical machine in every possible way that I could detect. And so we're going to run virtual machines on these servers, and that adds to the ability of flexibility in the system. And so in this particular case, what used to be bundled in the routers or the switches now has been completely unbundled. I have a forwarding plane that's forwarding packets, and I have the brains or the control program that controls that running in virtual machines. Oh, there's my cattle. And the I/O devices, I just treat them as commodity. And in fact, we're going to build those I/O devices out of commodity. And I'm going to do this over and over and over. For every one of those 300 devices that used to live in the central office, the ones that I don't end up throwing away, I will run the code inside of a virtual machine, inside of that very same infrastructure as I was before. So that's the basic idea. Software running in virtual machines using commodity switching fabric across the top, and I've reduced all that heterogeneity, closed, bundled, difficult to manage system into something much more manageable. So basically what we're doing is we're trying to take, oh, I forgot to say, taking all those functions out of those boxes and putting them into virtual machines has been given its own 3-letter acronym called NFV, which stands for Network Function Virtualization. You take a function that used to live in hardware and you run it in a virtual machine on a commodity processor. That's all it means. And so what basically we're doing is we're trying to take the best of what the cloud gave us, commodity hardware and software, the idea of taking software out of hardware and sticking it into virtual machines, and the idea of programming the switches to connect everything together. And that is the sort of the unifying theme of CORD. And we're just going to put a name on that. We'll call it everything's a service, not just software, but everything is a service. And so if we go back, and this is a slightly different picture. I should have said a minute ago when I was showing the cattle and so on, that's a picture I got from a colleague at AT&T. I really like the way he did that, so he lent me his slide. But here's my more boring slide. Basically, we've just got racks of computers, and over on the edge, well, this edge, is the I/O devices that go to your home. So fiber to your home is over there. There is what's called a leaf spine switching fabric. It's got a set of leaf switches that are the top of every rack, and they bounce up to a spine switch to get me through. And every blade in the I/O chassis is basically a pizza box with 48 fiber ports on it that is the very port at the end of your fiber connection if you only had fiber connections to home. Some places there's fiber, AT&T's trying to roll it out, Verizon's already done it, but that is literally the fiber plugging into one of those ports is the other end of the last mile of the fiber that we're all hoping and waiting for. And that box is commodity. It's been reduced to a merchant silicon a chip, and all the logic that used to be in there is now running in software. There are actually vendors that will build these white box switches. Acton is the one that we've been using. I'm only showing you the picture just to give you some sense. These are 32 ports, 40 gigabits per second on each port, pretty hefty devices. But what I wanted to show you is if you crack one of those open, you will find at the very base a chip. And it's not going to be an Intel chip or an ARM chip, it's going to be a Broadcom chip. So that's sort of the equivalent here in the switching world, is that there will be commodity chip vendors or merchant silicon vendors selling you forwarding chips. And then there's layers of, it turns out to be open source software running inside of each switch, basically, running, taking the instructions from above and programming them into the switches. So it is open source software all the way down to the chips. This is basically the only point I was trying to make here. And there's more acronyms there, but don't worry about them. OCP is it's actually a consortium of companies that are trying to, it's called the Open Compute Project, but basically they're trying to build these merchant silicon devices. Now, that's the hardware. I'm going to keep telling you everything's the software. It's hard to show you software, except in PowerPoint I can draw different colored boxes. Basically, there's three large pieces here. One of them is ONOS, which I mentioned before. That's the operating system that manages the switches, and it runs a set of applications, just like Android runs a set of applications, except these applications program the switches. And OpenStack happens, ONOS is open source. OpenStack happens to be an open source bit of software that manages servers and instantiates virtual machines. So it's kind of the counterpart on the server end. So I've got open source software controlling the switches, open source software controlling the servers and setting up virtual machines. And I'm going to layer something on top that is adopting the everything as a service model, whether that service was implemented in the switches or in the servers. And it's trying to basically unify everything, because as much as I can make everything look the same, then I can start plugging and playing and hooking things together in different ways. And that's kind of the value of it. So that's the software stack. It sometimes helps people to kind of tie things together. They can see there literally are layers of software, but that's not really the interesting way of looking at it. The interesting thing to think about is how we took the hardware that used to be in the central office and we blew it into bits and we disaggregated it into smaller and smaller pieces. And so you maybe didn't realize this, but this is the path that your packets follow. And it's a little different if you're on your provider's a cable company, but if it is a telco, you have, and now it's acronym heaven here. We've got a CPE, that's the consumer premises equipment. That's your home router. There's an optical line termination. That's the device that your fiber link plugs into that lives in the central office. And then there's a BNG, which is the broadband network gateway. That's basically the transition from the access world to the internet world. And it's a big, expensive, complicated, bundled product that some people would happily sell you. And it basically is the manifestation of that tension I was telling you about. This is where everything gets bundled. And so that's the thing we're going to blow up. And so I'm going to go through this kind of quickly and just hopefully give you a little bit of the sense of it. We're going to disaggregate it. We're going to take the home router and we're going to break its forwarding capability off from the software control of the forwarding, and we're going to move the software forwarding control back into the central office. And so you will have a virtual machine running on your behalf that lives in the central office controlling your home router. And all the policies, the parental control, firewall rules, intrusion detection, everything that you might, if you ever logged into your router, you would be logging into a virtual machine back in the central office instead. Everything that you might set up there, poking holes through so that you can do video games. Apparently that's what they do. So we're going to do that. And then we're going to do the same thing with the OLT, and that is, in fact, the optical line termination is that one unit box, 1U box that I described earlier, and it's going to have a control plane piece, and it's going to control the merchant silicon switching. And then there's a big Ethernet aggregation switch in there too. I'm not going to really do anything with that. I'm going to go to the BNG, and I'm going to do the same thing. It's got a data forwarding capability, and it's got control software. Except now the control software is going to be an application that controls the switches. I'm going to call it vRouter. By the way, VSG stood for Virtual Subscriber Gateway. It's your gateway to the world. VoLT is virtual optical line termination. vRouter is like a router, except it's virtual. It doesn't actually live in a box. It lives in it's entirely software. And it turns out that there's other per subscriber functionality that we're going to move back into the container. And the last piece is every time you connect, you power on your home router, you have to authenticate yourself to your service provider so that they know you're paying your bills. And we have to do that earlier. That's normally not until the BNG, but we have to do it earlier because I've actually spun up a virtual machine on your behalf, and I would hate to have done that and you didn't have rights. So basically what used to be one big lumpy function has now been split into 3. And in fact, 90% of the code just went away because 90% of it was in that box because the vendor put it there to sell a feature to somebody else. It is not something that you would use. So this just drastically reduces the complexity of the system. And oh, by the way, it really turns out that the forwarding plane or the data plane of the BNG is implemented in the switching fabric. And so if you remember that switching fabric with all the leaf spine switches, that is where all of that capability ends up. All right, I realize that was a little fast, but the point of it is these things start to break apart pretty naturally if you do that. So we've disaggregated. How are we going to put that back together again? This is the equivalent of the guy who walks between the aisles of the central office and puts a piece of hardware in and then wires it to somewhere else. All right, that was a very slow, time-consuming, labor-intensive problem activity, and we just got rid of the hardware. It's now our virtual machine. It could live here, and a second later, it could live over there. And I could spin hundreds of them up instantly. So it's much, much faster than putting a server into a rack. How do you actually go about doing that is the real question. How do you manage the complexity of what I've just given you the capability of doing by breaking all these things down? Well, here's the magic. It's the message of the talk, which is the power of abstraction. Computer scientists do 2 things. They invent complicated algorithms that solve very narrow problems. And just the example that I gave you earlier, there are algorithms that will find the shortest path across a graph, and that is used for network routing. But the other thing that we do is we build abstractions. And so this is really what the how part of putting all those pieces back together again. You just have to think about it the right way. Because if you think about it the wrong way, it will become increasingly complex, and that's going to slow you down. So there's a quote from John Donovan, who's the executive vice president of AT&T, that's trying to steer that ship in this new direction. And at a conference, I am positive I heard him say abstractions are like pixie dust. They provide the magic that makes systems work. Barbara Liskov, a Turing Award winner. Turing Award is computer science Nobel Prize. Modularity based on abstraction is the way things get done. And I like the Don Norman quote, the ability to master complexity is not the same as the ability to extract simplicity. This is how do I extract simplicity, because I don't do that right, I'm going to end up with a very complex system. And this is one of the things where time will tell if we've done this right, but we have a line in the sand. Basically, I give you a chord graph that says function service A depends on service B depends on service C. And literally, those are services, so you become a tenant of the service, just like you'd become a tenant of a service that Amazon or Google would offer you, except now services are becoming tenants of other service, and you can construct a graph. And then you put some annotations on the edges that say how you want things to behave, and out turns the crank on the abstractions, and you get the behavior out of it that you wanted. So it's basically just a nested set of abstractions, or they're sometimes called models. An instance is like a virtual machine. I scale something up with a set of virtual machines. That's how I get high performance out of it. That's called a slice. It's a set of virtual machines and a set of virtual networks. I put a controller on it, I get a service. I link a set of services together, I get a service graph. So hopefully you get the idea. And that's very simple, but that's the way that you have to do it, or else you end up with a very, very complicated problem. And again, apologies, maybe we can drill down a little bit more if you like, but it's all about the abstractions that make that work. We build pods. We can't go in and just rip the entire central office out, but we can get a toe in the door and give you a small delivery in maybe one rack's worth of hardware that's built like this. And so we built a small pod that we use to show how this all works. We have, in fact, then run it in a field trial with AT&T, and you can be at home and watch television, or you can browse the web on your laptop, and basically you're coming in through a fiber network connected into one of those OLT devices that's part of this cluster that's under the control of the open source software. And if you kind of set this on its side and looked at it, you would find that you're going from your iPad or your home device through a virtual network under the control of an application. You hit a virtual machine that's running on your behalf, and you go through another virtual network under the control of another application, and that will get you out to the internet. And so if you were to look inside of those clouds, you would find the switching fabric on the one hand, and you would find that OLT device on the other. And everything I've been talking about up to this point has been what's going on in the residential part of the access network, but there are counterparts with a different set of services in the mobile case and in the enterprise case. So the same principles apply there as well. So let me try to tie this all up with the following, returning to my virtuous cycle again. As we left it, Uber was running on the cloud. What I basically just described is taking the cloud out of the data center. It's locked into the data center right now. And there are a lot of them, but they tend to be quite far away, and they tend to be huge. And basically, we've replaced it. What we're building is the edge cloud. The cloud doesn't just live in data centers and warehouses. The cloud actually now lives throughout the entire internet. And that is a combination of that commodity compute and the commodity switching. And what's that going to enable? The next big thing, Internet of Things. So if you've heard this phrase, this is basically the ability to connect everything from your refrigerator to your thermostat to your toaster to the internet and control them. And it's not just that you can control them, that's the easy stuff. It's the fact that all the data that they're producing is being collected, shipped back up into the cloud and processed, and then it gets smarter. And so that's really what this is about. And I don't want to have to ship it all back to the warehouse because there was that narrow northbound pipe. I can ship it as far as my central office, and I've got some compute capability there, and I do some early analysis and ship summaries on up. So Internet of Things is what's going to happen. And what enables it is commodity hardware, open source software, and these unified abstractions that pull all the pieces together. So this is like I said, it's a project. You can probably tell that AT&T is involved, Verizon's involved, Comcast, several international carriers, and the vendors are there too, because of course they want to keep tabs on this and try to understand where the new business models are going to fall out of this as well. Although it is certainly disruptive to a lot of what they do today. So if you're interested, you can go find more on the internet as well. So with that, I think I will stop and take some questions for a little while. Thank you.
Thank you, Larry, so much. I could have listened to that longer, but we have to call it a night. We have time for a few questions. So Darby and I are going to go grab some mics, and we'll come to you with the microphone so everybody can hear.
Good. Yeah, thank you. I don't know, maybe turn that down so I can see.
Works and you're right, that works. Okay, and you know, you're hearing about things that have been shut down and they're not working. Is this going to make it easier or harder for that to happen?
We will still be on the same. And trust me that the interior of these, the telcos are last to do this sort of thing because they are so conservative in what they do. They're offering, you know, emergency services and so on. So yes, there is. Everyone understands that there's a risk there, but a huge amount of attention goes into isolation of various factors. And so virtual machine technology is about isolating you in a virtual machine that is as solid and protected from the other virtual machines as physical hardware would be. And virtual networks actually is the counterpart in the network that's just as important. What has to happen now is the operator is pretty much manually changing a set of parameters that says who can talk to who. And you got to get this right, but once you have it right, you get the operator out of the loop. And that's really what it comes down to at the end of the day. There's a great story about 9/11 that the network was actually, the internet was actually more reliable on 9/11 because the operators went home. Yeah, so I think that's, yeah, good, very good point, but I think you know, in the race, that has to be the next step.
Since these are private companies, I may not completely understand the term. You're talking about an open source development. Since these are private companies, and I may not completely understand the term, you're talking about open source development versus proprietary development among these companies. Since companies are so competitive, why is this happening in an open source context? And will that be better for the individual companies?
Yeah, that's a great question. But this is what's happening. So if you do this with open interfaces, everyone understands that you've opened things up for innovation. What everyone believes to be the case, and once you start down this path, you kind of have to play the game because everyone else is, and we're over that hump by and large, is the infrastructure that we all share. None of us particularly gets value out of it. Is what we want to be common. And there's always going to be value that you have to provide on top. So it's always your problem to figure out where that value is as a company. But the platform software is not where the value is. It's enabling you to do something that provides value. But every iteration of this loop, somebody used to be the app with value, they got turned into platform. So somebody does suffer, but a whole new market or business model emerges out of that. So just to turn it back into AT&T, for example, and they're not unique. Every single carrier is insisting. There's enough progress been made right now on all of this that you could go off and take it closed source and go do it, but they're not going to go. They're not going to fall for that one. They want the common part of this to be open source. There will be integrators. There will be people that harden it. And and hopefully when you do that, you will provide some additional value, and that'll be your business model. I'm sorry.
Well, back down at the commodity hardware, is there any value to future innovation down there at all, or what?
So those folks are working really, really hard to keep up with Moore's law and keep doubling the transistors. But it's all about getting scale out of that. I mean, if you think,
There won't be any incentive for them to work that hard if there's no margin.
and that's why you end up with it's commodity and you have a very, very, very small number of providers. All right, if you think back to the day that Honeywell and Spirit Univac and IBM and everybody was building their own hardware, and that's been reduced to a couple of flavors of hardware. But you now sell it at scale, and your margins are very, very small. But what you lose in market margins, you make up for in volume. I mean, Intel is a huge backer of this because they see this as a way of replacing all of that purpose-built hardware with their commodity hardware.
How long do you think the transition will take till, say, 2/3 of the central offices are use this new technique?
Good question. How long is it going to take? Wish I could remember exactly what John Donovan's targets are, but it's very, very aggressive. And it's not going to be, I probably shouldn't even use his numbers because he's shooting for something that's a little lower than what I just described, which is full bore Amazon, Google Cloud capability. His steps are a bit more baby steps. I would say this has been going on for 5 years, and maybe we are approximately halfway through the transition. But it's the companies that we're talking to are doing field trials this next year, and that is supposed to lead to product. And if you didn't have a fiber rollout last time around, because your AT&T and Verizon did, then you're very highly incentive to do this. I'm sorry.
Are the computer systems being commodified because we're not doing analytical stuff in our systems anymore, but it's just packet of information going from, say, Amazon to my house to a friend's house and things of that nature? Or is there actually analytical, scientific work on these computers?
Oh, you can do scientific work on the computers. What this is all about is that you get very limited value out of special purpose-built hardware. It doesn't solve your scientific problem as fast as if you built hardware to solve exactly your scientific problem, whatever it might be. And the same goes to forwarding packets, right? There are application-specific integrated circuits, ASICs, in the switches and servers of today. And the story is, you know what, if that was commodity, we'd be a little bit slower, but then we'd have all these advantages of scale. So purpose-built hardware can always be made faster for one purpose. Commodity will ultimately beat it because it's got its economies of scale.
One more question?
Someone has a mic somewhere. Oh, there it is.
All of your last mile slide connections were passive optical network, whether they were serial connections or cloud connections. How fast is that proliferating? And we got PON in New Hampshire a few years ago. It cost Verizon $500.
Will be Verizon. You deliver it by fiber to an apartment complex, and then there's a copper distribution in that. So there's a whole bunch of technologies for which the commodity boxes are being built. But I think ultimately, and I didn't have time to talk about it, the wireless technology fits exactly the same model. And that'll be huge. That'll be bigger than anything I described so far.
Do you have one more question be asked? This gentleman's been standing back. If you'll
What's the potential relationship from what you said to the ability to get fast internet to third world countries?
Great question. So exactly what you want to do is to be able to metaphorically parachute in a partial rack of this commodity hardware. And so Facebook in particular has a project that is exactly mirroring what we're doing that's very much like this. Yeah. And so that is a huge spin-off value that you get out of this. And it's much, much less expensive and it's scalable. I mean, you can build entire, 16 racks of this stuff, or you could build 2 servers with the exact same software technology.
And the same question regarding service to rural America.
Yeah, same thing. Yep. And then it would probably be fixed wireless. There would be a good option as well.
Okay, thank you so much. I know a lot of you still have questions, so you're welcome to approach Larry one-on-one with those. And I do want to announce next month's talk. It's called Visualizing a Billion Data Points by Dr. Carlos Scheidegger. He's a professor of UA Computer Science. That's January 12th. In the new year, 2017, and it's at 6:30 p.m. And if you didn't get a chance to write that down, we have flyers out there that you're welcome to take. All right, thank you.